Is there a relationship between population density and mortality due to air pollution? My thesis question is there a relationship between population density and mortality due to air pollution? I predict that areas with higher population density will have higher mortality rates due to air pollution. This is because densely populated regions often have more vehicles, industries, and energy use, which contribute to poorer air quality and increased health risks. Top countries in mortality due to air pollution, units per million persons, is from nationmaster.com. Population density, people of square kilometers of land area, is from World Bank Group, data@worldbank.org. A 2022 study using data from Germany cities between 2002 and 2015 found that higher population density leads to increased air pollution. The researchers used advanced statistical methods to isolate this effect and found that as population density rises, concentrations of nitrogen dioxide and particulate matter also increase. Specifically, a 1% increase in density results in a 0.25 rise in nitrogen dioxide and a 0.08 rise in PM10 levels. These pollutants are mainly caused by traffic and industrial activity, which are more concentrated in densely populated areas. The study confers a clear positive relationship between population density and worsening air quality. The scatter plot demonstrates a moderate positive correlation between population density, people of square kilometers of land area, and air pollution mortality measured in deaths per million persons, evidenced by an upward trend where higher density regions generally show elevated mortality rates. Statistical analysis confirms this relationship. A correlation coefficient R of 0.65 indicates a meaningful association, while the linear regression equation y equals 0.48x plus 120 quantifies that for every 1,000 people per kilometer square increase in density, mortality rises by 48 deaths per million persons. However, the coefficient of determination R equals 0.42 reveals that population density explains only 42% of the mortality variation, emphasizing the role of other factors like industrial activity or healthcare access. The substantial variability in both variables, mortality, standard deviation equals 259.7 deaths per million, and density, standard deviation equals 241.3 people per kilometer square, is visible in plots dispersed points, with outliers, for example, low-density areas showing unexpectedly high mortality, highlighting regional complexities beyond density alone. The pie charts reveal distinct distribution patterns for both variables. For mortality due to air pollution, the data is right-skewed with 61 regions, 38.9%, concentrated in the lowest bin, 46 to 258.5 deaths per million, while only 20 regions, 12.7%, exceed 683.5 deaths per million. This skewness aligns with one variable statistics. The mean 373.9 exceeds the median 317, and the high standard deviation 259.7 confers significant variability. Conversely, population density exhibits extreme right skew. 140 regions, 89.2% fall into the lowest bin, 2 to 318.67 people per kilometer square, while only 3 regions, 1.9%, occupy ultra-dense bin, greater than 952 people per kilometer square. 145.7 drastically outweighs the median 78.5, and the standard deviation 241.3 reflects outlier-driven spread. Critically, all regions with high mortality greater than 896 deaths per million align with higher density bins, greater than 318.67 people per kilometer square, supporting the hypothesis that urban density intensifies air pollution health risks. However, the 42 regions in the moderate mortality bin, 258.5 to 471, despite low density indicate non-density factors. For example, industrial activity also contribute to mortality. The histograms illustrate pronounced distribution patterns for both variables. For mortality due to air pollution, the histogram is strongly right-skewed with 61 regions, 38.9% concentrated in the lowest bin, 46 to 258.5 deaths per million. Frequencies decline sharply. Only 24 regions, 15.3%, fall in 386 to 556. In the mere 8 regions, 5.1% exceed 896 deaths per million. This aligns with one variable statistics where the mean 373.9 substantially exceeds the median 317, and the high standard deviation 259.7 reflects extreme variability. The population density histogram shows pathological red skewness. 140 regions, 89.2% cluster in the lowest bin, 2 to 318.67 people per kilometer square, while bins above 635 people per kilometer square collectively contain just 3 regions, 1.9%. There's mirrors density statistics where the mean 145.7 drives the median 78.5 by 85%. And the standard deviation 241.3 confirms outlier dominance. Critically, the highest mortality bin, greater than 1,108.5 deaths per million, corresponds exclusively to regions in the top 0.6% density bin, greater than 1,585 people per kilometer square, reinforcing the urban density mortality link. However, 52 regions exhibit moderate mortality, 258.5 to 471 deaths per million, despite low density, smaller than 318 people per kilometer square, underscoring rules for non-density factors like industrial emissions. The box and whisker plots reveal critical distribution characteristics for both variables, strongly supporting the observed patterns in prior analysis. For mortality due to air pollution, the plot exhibits pronounced right skewness. The median 317 sits well below the mean 373.9, with the interquartile range concentrated in lower values, roughly 200 to 500 deaths per million, while the upper whisker extends sharply to 1,321 deaths per million, highlighting the high mortality outliers that align with urban hotspots. Similarly, the population density plot shows extreme skewness. The median 78.5 people per kilometer square is dwarfed by the mean 145.7, and the IQR, roughly 30 to 200 people per kilometer square, is compressed near zero, with the upper whisker stretching to 1,902 people per kilometer square, capturing ultra-dense outliers. These one-variable distributions directly explain the two-variable relationship. The high mortality outliers, top 5%, greater than 896 deaths per million, correlate exclusively with high-density outliers, top 1.9%, greater than 952 people per kilometer square, validating my hypothesis that dense urban areas intensify air pollution health risks. However, the moderate positive correlation R equals 0.65 and the limited explanatory power R equals 0.42 from linear regression reflect how outlier-driven skewness dominates the relationship, while low-density regions show wider IQR mortality variation, 250 to 500 deaths per million, underscoring rules for non-density factors like industrial emissions in rural areas. My hypothesis was correct. Areas with higher population density show greater air pollution deaths because of more traffic and industry, but some less crowded places still had high death rates, meaning other pollution sources also matter.